This is the Minimal 64X4 home computer designed by Karsten Herting, otherwise known as the YouTuber Slew4. Karsten claims that this is one of the fastest retro 8-bit computers out there, being 4 times faster than the Commodore 64.
With my previous video, I've released the Minimal 64x4, a DIY home computer with VGA and PS2 built out of logic chips. It's designed to be really accessible, easy to understand, and it runs at 8 MHz, packing 4 times the processing power of a Commodore 64.
That's quite a claim. In my experience, this is a fast computer. However, can we make it faster? Welcome to today's video. Way back when I designed my ALU for my PewDie1 Homebrew CPU, I mentioned that I wanted to create a video that dived deep into how computers do math, especially higher order math like multiplication. Well, that's what today's video is about. I'm going to be exploring how to do multiplication with software and then with hardware on the Minimal 64X4. I picked that platform much like I did in my previous video on the TMS5220 because it's an easy platform to hack and work with, and it's a really well designed platform, simple to understand. Before we get into it, just a word on the title for this video, a homebrew GPU for a homebrew CPU. Yeah, I took a little liberties with the title. What I'm making today isn't really a GPU in the way that you think about GPUs for modern computers. Instead, it is more akin with a math coprocessor that you would install in a retro computer. However, it is being used in order to accelerate the calculations needed to render various images on the Minimal 64X4, and so in that sense, it's a graphics accelerator, much like a GPU is. However, unlike a modern GPU, it doesn't have parallel processing, it doesn't do multiple different kinds of mathematical operations. It is focused on doing one thing and doing one thing fast. Given that, I hope you'll forgive me for taking some liberties. It's all in good fun. So, without any further ado, let's get into it. Let's begin with something familiar, long-form multiplication like what you learned in grade school. Take a problem like 14 times 13. In base 10, we multiply the entire top number by each digit in the bottom number, writing down the 2 partial product rows, shifting the second row left 1 place because it represents the 10 place value of 10 in the second value. And then add the rows together to get the final result. Pretty straightforward, much as you remember from early grade school. Now, let's take the exact same multiplication problem and rewrite it in binary. 14 in binary is 1110. 13 in binary is 1101. Right away, you can see something interesting. We went from 2 decimal digits to 4 binary digits. That means instead of 2 partial product rows like in base 10, we now have up to 4 possible rows, 1 for each bit of the multiplier. But the process is the same. For each digit of the multiplier, produce a partial product row, shift it left the appropriate amount, and add everything together. Here's the key simplification in binary. Each bit is either 0 or 1. So, for each bit in the multiplier, if the bit is 1, the partial product row is simply the multiplicand shifted left by the bit's position. If the bit is 0, the entire partial product row is 0. Binary multiplication is fundamentally just a shifted add algorithm. For every on bit in the multiplier, we add a shifted copy of the multiplicand. For every off bit, we do nothing. And this maps into very simple code. Here is the classic shifted add algorithm written in Python. You can see that this code is fairly simple. You take 2 inputs, one the multiplicand, one the multiplier, initialize a result variable with the value 0, and then we start a loop. In the loop, the first thing we do is check whether the rightmost bit of the multiplier is 1 or not. If it is 1, then we add the current value of a to the result. Regardless of what happens in that if branch, we then shift a to the left once to kind of represent how those partial product rows are being shifted left. But then we also shift the multiplier variable b to the right. This is kind of a convenient way to scan through the individual bits of the multiplier to determine whether they're on or off. As we go through each loop, you can see that a is being shifted to the left as it should be for the multiplication algorithm, and the shifting of b to the right allows us to use a simple B and 1 bit mask in order to determine the value of the bit in a particular position. When the loop is done, return the result, and thus you have a multiplication. There's one more thing I want to highlight about multiplication that is very relevant when implementing it for computers. If we look here at the long form multiplication of two binary numbers, you can see that the result of multiplying two binary values together requires more bits to represent the results than it took to represent the multiplicands. In fact, the number of bits required to represent the product of two binary values is equal to the sum of the bits of the values that were multiplied together. This fact can then be generalized when implementing multiplication. That is, if you want to implement a method for multiplying two 8-bit values together, then the result of that method could be up to a 16-bit value. This insight will be factored in later when we implement multiplication in both software and hardware forms. So let's see how I implemented this software approach to multiplication for the Minimal 64x4 in its assembly language. This is the math library I wrote for the Minimal 64x4. It focuses on 16-bit multiplication support, taking two 16-bit values and producing a full 32-bit product. Internally, everything is built around a 32-bit accumulator, so we don't lose any bits of the results. At the top of the file, you can see several zero-page variables that are used within this library. Probably the most important one is this underscore mul underscore result. This is where the result value will be calculated. Other important values are the multiplicand. You'll notice that this is a 32-bit value. The reason why this is a 32-bit value as opposed to 16 is if you recall back to the Python representation of the software multiplication algorithm, you'll remember that one of the values, the multiplicand, is shifted right for every bit that we're exploring in the multiplier. Since there are 16 bits, that means the multiplicand is ultimately going to be shifted left by 16 bits, meaning I need 32 bits in total in order to represent it. This counter is used in order to count the number of times we're going through that loop of checking out a bit within the multiplier and shifting the multiplicand left by that number of bits. And finally, there is this variable here, a sign flag, which is used when I'm doing signed multiplication. A little bit further down, you see this preprocessor flag, use accelerator. When this symbol is defined, this file will be compiled using the hardware accelerated path that talks to the multiplier board. When it's not defined, we compile the pure software implementation of multiplication instead. For now, we're going to stay entirely on the software-only path. This flag actually gets defined on the command line when using bespoke ASM in order to compile this file. The public API for 16-bit multiplication lives near the bottom of this file. The first one is this ml16 underscore unsigned underscore multiply. This is simply a wrapper around a core function called multiplication underscore core, where actually all the work occurs of doing a multiplication. What this wrapper does is just provides a public API to software outside of this library that is using it. Specifically, it allows the multiplier and multiplicand to be passed on the stack, and then it is placed into the various zero-page variables that I already described as needed. When the multiplication is done, then the result is written back to the stack, the 32-bit value of the result, replacing both of the two 16-bit values used as the input. The other function is this ml underscore signed multiply function. What this does is a signed version of the multiplication. The core is still the same. I'm still using the same multiplication 16 underscore core, but what I'm doing is wrapping that core with something that determines if either the multiplicand or the multiplier are themselves negative. If one of them is negative, then we know the result is going to be negative. This code looks at both the multiplicand and multiplier, determines whether the result needs to be negative, and if either of the values are negative on input, converts them to a positive value, and then passes that positive value to the core function in order to do the multiplication of two positive values. It remembers the result needs to be negative, and if it does, it will convert the result into a negative value before passing it back onto the stack for the user to consume as it needs to consume. So the basic use of both of these functions, at least from the user perspective, is they push two values on the stack. They call the desired multiply function, whether it be signed or unsigned, and then they get a 32-bit product back on the stack. Let's take a look at this core function that we're talking about. Now let's look at the software implementation of multiplication. Multiplication 16 underscore core assumes that the mul_multiplican already holds a 32 value whose lower 16 bits are the multiplican to be used for this operation. And then temp_val2 holds the 16-bit multiplier. It starts by clearing the result variable where the results are going to be put into. Then there's a small optimization. It checks whether the most significant byte of the multiplier is 0 or not. If it is 0, then we only really need to do 8 iterations of the multiplication loop in order to handle the least significant byte of the multiplier. If it's not 0, then we need to do the full 16. Either way, we populate the counter variable with the number of iterations that we're going to do, either 8 right here or 16 right there. Then we get into the main multiplication loop. The first step is to determine if the multiplier has a 1 in the least significant bit position, and that's what this code does here. If it does not have a 1, then we go ahead and skip adding and we move on to the next step. But if it does have a 1, then we add the multiplican as it currently stands into the results variable. You'll note that this instruction right here is not a normal minimal 64x4 instruction, and if you look closely you can see it's a slightly different shade using the syntax highlighting that Bespoke ASM implements. What this actually is a macro that I have created for the minimal 64x4 instruction set. The native instruction set of the minimal 64x4 does not have an instruction for adding a 32-bit value that's in 0 page to another 32-bit value that's in 0 page. So what this macro does is actually create that instruction by sequencing a few other instructions such that the net effect is adding two 32-bit values. Moving on, once the addition is done, or if we're skipping the addition, then we need to shift the multiplican left by 1 bit, and that's what this instruction does here. The minimal 64x4 does have a native instruction for doing a 32-bit left shift within 0 page. Finally, we need to shift the multiplier right by 1 bit. To do that, first I clear the carry bit so that when I do the rotate right, what gets inserted into the most significant byte is a 0. Then I do a rotate right on the most significant byte, which then populates carry with the bit that needs to be then shifted into the least significant byte, and then I do a rotate right on the least significant byte, which pulls in that bit that's in carry and then pushes the bit that's going to be discarded into carry, which then we ignore from that moment on. Finally, decrement the counter, and if the counter is not 0 yet, we repeat the multiplication loop. Otherwise, we return, and that's the multiplication. Next, let's look at a program that I wrote that will exercise this multiplication to demonstrate the speed difference between the software and hardware. And that program is simply the Mandelbrot program. This is a fairly standard algorithm. I'm not going to go over detail of the algorithm here because there's plenty of resources out there if you want to understand how the Mandelbrot set is calculated. But the thing I'll point out here is that this algorithm does use the signed version of the multiply function. Now you may ask, how can you do a Mandelbrot algorithm using integer multiplication? The answer here is we're using fixed point arithmetic. You can see that right here. This scale bits variable right here sets the size of the fractional part for the fixed point arithmetic. Here we're using the significant 9 bits of a 16-bit value will represent the fractional part of that value. That combined with the scale factor sets the dynamic range of the calculations that we're doing. These two values together comfortably gives us a range of about -2.5 to +1.5 for the area that the Mandelbrot set will be calculated for. The other important parameter is this max iterations in combination with the escape radius. The max iteration tells us the number of times we're going to try to see if the value that we're calculating is getting larger than the escape radius. which if it does, by definition, it is not in the Mandelbrot set. If we get to the max iterations of 20 and we're still within the escape radius, then that point is in the Mandelbrot set. What this does is tell you how many calculations we're going to do approximately. Now remember, the minimal 64x4 screen has a pixel dimension of 400 by 240. That's 96,000 pixels that we're going to have to calculate whether it's in the Mandelbrot set or not. For every one of those pixels, we can iterate up to 20 iterations. Most of those pixels, admittedly, they are going to escape on the first iteration. Just that's the way the Mandelbrot set works. But when we're getting into where the pixels are close to being within the Mandelbrot set, you will actually see, when I show this later, you'll actually see the calculation slowing down because we're doing many more iterations until we determine that, yes, this point is actually in the Mandelbrot set. But that does give you a sense of how many calculations we're going to be doing. We're going to be doing tens of multiplies per pixel, potentially, depending on whether it's in the Mandelbrot set or not, across 96,000 pixels. That brings us to the scale of 500,000 to 1,000,000 multiplications per frame. My point here is that this ends up being a real good demonstration of whether the hardware multiplication is speeding up things for us or not. One thing I should make clear, if you scale through this file real quick, you can see that the Mandelbrot set code is doing a lot of other things than just straight up multiplication. And so, just to set expectations here, when we look at the software multiplication speed and then compare it to the hardware multiplication speed, we should expect a speed up. But there is still a lot of overhead that needs to occur in order to create this image. And so the speed up may be noticeable, may not be noticeable. We'll see. And to that goal, let's move on to trying this program out on the real hardware. Okay, let's go ahead and test the Mandelbrot software here on the Minimal 64X4. Now, reminder, this is the version of the Mandelbrot code that is running based on software multiplication. So let's see how long it takes. I've already compiled the software and loaded it onto the Minimal 64X4. So all I have to do is type it in and hit go. And let's just see how this performs. Okay, that very much looks like the Mandelbrot pattern. So let's take note of the time, how long it took for this software multiplication version of Mandelbrot to take, and let's see if we can make that faster. Now that we've seen the speed of software multiplication, let's look at how multiplication can be implemented directly in hardware. And to make this concrete, I am going to build out a 4-bit multiplier circuit to demonstrate this process. At the heart of a binary multiplication is a very simple observation. Multiplying 2 bits is the same thing as doing an AND operation. If you look at the truth table for multiplication, you'll see this pattern. 0 times 0 equals 0, 0 times 1 equals 1, 1 times 0 equals 0, and 1 times 1 equals 1. But if you look at it closely, that's exactly the same truth table for the logical AND operation. So, if we want to multiply 2 multi-bit numbers, as I said, 2 4-bit values, the first step is to generate all the partial product bits by using nothing but AND gates. Here on my 4-bit multiplier schematic, you can see I'm using a whole grid of 74 AHCT08 AND gates. I chose the 74 AHCT family in order to make it very fast. It is a faster version of the HC family of logic chips. On the input side, at J1, bits A0 through A3 are the 4 bits of the multiplicand, and B0 through B3 are the bits of the multiplier. Each A cross B combination gets its own AND gate. For example, A0 and B0, A1 and B0, A2 and B0, and so on. If you follow the wiring in the schematic, you'll notice that the outputs are neatly grouped into rows. Each row corresponds to one bit of the B multiplier, just like the partial product rows we drew earlier in the binary long multiplication. And because each of the rows represent a higher power of 2, the wiring automatically shifts these rows to the left as we move downward through the schematic. Generating partial products is the easy part. The harder part is combining all those shifted rows into a single result, and we do that with adders. In this design, the heavy lifting is done by 74 HCT 283 4-bit adders. Each adder stage sums a set of bits that are all aligned in the same binary column. And just like long multiplication, when the column overflows, the carry propagates to the next adder stage. On the schematic, the AND gate rows feed into the adders in a diagonal pattern. And you can see the signals funneling down into all the adders, and the carries ripple downward and to the left. This creates what digital designers call an adder cascade or an adder array. Altogether, this results in a purely combinational structure where, first, each AND gate outputs a 1 or a 0 depending on whether its bit pair should contribute to the final sum. Second, the adders systematically combine all those partial product bits column by column. And third, the carry signal ripples through the cascade until the final 8-bit result is stabilized. The output header J2 on the schematic, labeled R0 through R7, carries the final 8-bit result of the 4x4 multiplication. And because we're multiplying two 4-bit values, we get an 8-bit result. So an 8-bit multiplier needs to output 16 bits, and that's exactly what we'll build for the minimal 64x4 in the next section. This 4-bit example shows the entire mechanism on a single sheet of the schematic. And in a moment, we'll scale this up to a full 8-bit hardware multiplier card that plugs directly into the minimal 64x4. What you see here is a breadboard implementation of the 4-bit multiplier schematic that you just saw. There are two additions to the schematic, admittedly. One is the input switches. In the schematic, you actually just had an input port. You can think of these outputs as the port themselves. And then second, the output is piped through a 74LS245 to power LEDs to display the actual answer. Other than that, the schematic, the implementation is the same as the schematic. You'll note I use different color wires to represent different things. The input on the left is the yellow wire, so you can see everywhere that the yellow wire is interacting with it for these AND gates. The input on the right is the blue wire, so you can see how it interacts with all these AND gates. Here are the adders, and the output from the AND gates that go to the adders are the green wires. The output of the first adder, or the first stage adder, are these orange wires. The output of the second stage adder is the purple wires, and the final stage adder is these white wires. One thing that might be interesting to know is the final output is composed of 1 bit from the AND gates, 1 bit from the first stage adder, and 1 bit from the second stage adder. You saw this in the schematic. It happens due to the shifting that you saw in the long form version of the multiplication algorithm. Well, let's try this out, see it work. Let's start off with multiplying 2 times, well, right now 2 times 0, so you still get 0, but let's multiply it times 4. There you go, that's 8. So position, it's bit 3, so that's 8 in value. Let's change this to 3 times 4, and you get 12. 3 times 5 is equal to 15. Let's do something that will spill over into the higher nibble. Let's make this 7 times 5, and you get 32 plus 2 plus 1 is 35. Let's go for the maximum value of multiplying f, or 15, times 15. And there you see what you get is E1, which is the maximum value you can get from a 4-bit multiplication. I also made this other version of the multiplier circuit. This version, you can see, is the exact same circuit, but I condensed it down to a single PCB using some surface mount ICs. Otherwise, this is the exact same circuit as you saw in the schematic. In fact, here is the input ports, here's the output ports. And in this case, the input switches go to those input ports and the LEDs come from the output port. You can see that it works just the same. Here we're going to multiply 10 times 4 and you get 40. So you can see that this multiplication circuit really does work, right? It does exactly what you expect it to do. And so let's get into seeing how you can use this in order to accelerate your computer. Now that we've seen how multiplication works in hardware at a conceptual level, let's zoom out and look at how it turns into a real usable expansion board for the Minimal 64X4. What you're looking at here is the full schematic for the 8-bit hardware multiplier card. At a high level, this board does exactly 3 things. First, it accepts 2 8-bit values from the CPU. Second, it multiplies them entirely in combinational logic. And third, it presents the 16-bit result back to the CPU in a clean memory mapped way. There's no microcode, no state machine, no clocked math happening here. Once the inputs are latched, the result settles after a small amount of combinational propagation delay. Let's start at the left side of the schematic, because that's where the multiplication actually begins. These large grids of 74 AHCT08 AND gates form the partial product plane. All of those partial product bits then flow into this central hill of 74 HCT 283 4-bit adders. These chips do the real work of collapsing dozens of single-bit partial products into a clean 16-bit result. Carries between partial products ripple downward through the array. And just like we discussed previously, the carry chain is the limiting factor for speed here, not the AND gates. That's why I chose the HCT 283s. They're fast enough, easy to source, and very well behaved electrically in this kind of design. Now, because this is a shared system bus, we don't want the CPU signals directly driving this big combinational network. So the inputs are latched into the 74 AHCT 374 octal registers. Operand A goes into this register, operand B goes into that register. When the CPU writes to the A or B register, the values are captured from the host system's data bus and stored in such a manner to continuously present them to the combinational logic of the multiplier board. So, those latch values feed the AND plane in the add array. On the read side, the result bytes are continuously being asserted by the terminal adder or AND gate where appropriate for that bit. Because these values can't be written to the host computer's data bus at all times, the result values are arbitrated by the 74 AHCT 245 bidirectional bus transceivers. These serve 2 purposes. First, they electrically isolate the multiplier board from the bus when it's not selected. And second, they ensure we never have multiple devices writing to the bus at the same time. The 74 AHCT 245s are then used to control when the results are asserted to the host computer's data bus. This is especially important on systems like the Minimal 64X4, where the expansion devices must be very well-behaved citizens, only writing to the data bus when their memory address is active. One important design choice here is that the multiplier core itself is purely combinational. There's no start signal, there's no done flag, there's no wait or ready line. As soon as valid inputs are presented, then the values are simply calculated through this combinational logic. And given that these chips I use do have propagation delays for their various functions, there is a finite propagation delay we need to account for. On this board, the multiplication itself is entirely combinational. So delay is simply the sum of gate delays along the longest path. Starting at the input latches, the operand bits come out of the 74 AHCT 374s in about 5.6 nanoseconds after the last value is latched into the board's memory mapped address. Those bits then pass through the layer of AND gates, the 74 AHCT08s, which add another 4.2 nanoseconds in order to do all of these logical AND operations. If you look carefully, you realize that all of these AND operations are in parallel with each other. So we only need to consider one gate delay time here. From there, the slowest path is the carry chain through the adder array. Even though there are 14 adders on the board, they're not all in series. The longest carry path passes through 8 74 HCT 283 adders, starting with the least significant byte being added, propagating through the high bytes of each additional stage. The slowest operation in a 283 adder is the carry bit propagation. Each of these 74 HCT 283 adders takes about 19 nanoseconds in order to propagate a carry. So, the worst case timing is if every adder in this path had to propagate a carry, resulting in a total delay of 152 nanoseconds. Add it all together, and the worst case settling time is about 162 nanoseconds from the latch edge to a fully stable 16-bit result. On the 8 MHz minimal 64x4, that's just 2 CPU cycles, orders of magnitude faster than the roughly 1300 cycles it takes to do the same multiply in software. Of course, there needs to be more clock cycles dedicated to when the software latches values into the board and reads values out of the board, but that will come nowhere close to the number of clock cycles needed for the software multiplication altogether. And that's why this board works so well. From the CPU's point of view, multiplication goes from being a slow subroutine in software to something that's effectively instantaneous. Down here is the address decoding logic. This board uses 74 HCT 688 magnitude comparators to match the high address lines against a selectable pattern. That pattern is what allows the host computer to select this board and make it active for various operations. For glue logic and timing, there's a small ATF16V8 programmable logic device. This chip generates the internal strobes, controls the output enables, and inserts the INH inhibit line at the exact right time so the host computer's RAM and ROM stay off the bus when the multiplier board is writing to the data bus. The key point here is that from the CPU's perspective, this board looks like any other memory address, just that when you write values to 2 input addresses, these other 2 output addresses will contain the result of multiplying those inputs together. Furthermore, another benefit is that in order to calculate the multiplication results, no CPU time is actually needed. The CPU time is just dedicated to the memory map operations. Okay, up to now, what we've been talking about is 8-bit multiplication. But early in this video, we were doing 16-bit math. So the obvious question is, how do we use an 8-bit multiplier card in order to multiply 2 16-bit values? The answer is that we do exactly what long multiplication has always done. We split the problem into smaller pieces and carefully manage the carries. So, if I want to multiply 2 16-bit values, A and B, we start by splitting each 16-bit operand into 2 bytes. A1 is the high byte of the first operand, and A0 is the low byte. Likewise, B1 is the high byte, and B0 is the low byte of the second operand. Now we do long form multiplication like before. But keep in mind here that each digit is an 8-bit value. We begin with the lowest partial product, A0 times B0. First thing to note is that even though A0 and B0 are only 8 bits each, an 8-bit multiplication produces a full 16-bit result, which is why the upper byte of the result has to be carried forward. The low byte of the result becomes byte 0 of the final product, and the high byte will be added into the next column. Now we generate the 2 cross terms. First, A1 times B0, and then A0 times B1. Each of these is also an 8x8 multiply, and each once again produces another 16-bit result. Note that in both cases, one of the multiplicands is in the high byte position, so that means that both of these partial products are shifted left by 1 byte. This is the same as how long-form multiplication works in decimal. However, you don't typically isolate the partial products of specific digit combinations like we are doing here. You implicitly add them together in your head as you're doing that long-form multiplication. Finally, we compute A1 times B1, the high byte multiplied by the high byte. This partial product is shifted left by 2 bytes and contributes to the upper part of the result. At this point, all 4 partial products are visible. Now that we can see all the pieces, this is where the important details show up. Every partial product here is 16 bits wide. So the final result isn't formed by simple placement of partial products. It is formed by adding bytes together and propagating carries. Let's walk through this one byte at a time. Byte 0, the least significant byte, is simple. It comes directly from the low byte of A0 times B0. No addition is needed here, so it propagates down to the result. Byte 1 is the sum of 3 different byte size values. The high byte of A0 times B0, the low byte of A1 times B0, and the low byte of A0 times B1. Those 3 bytes are added together, and if that addition overflows, the carry propagates upward. Byte 2 is formed the same way, by adding 3 byte-sized values, plus any carry from byte 1. It is formed by adding the high byte of A1 times B0, the high byte of A0 times B1, the low byte of A1 times B1, plus any carry from byte 1. Again, this addition can overflow, and that carry propagates upward. Finally, byte 3, the most significant byte, is formed from the high byte of A1 times B1, plus any carry from byte 2. When you put everything together, the full product is just A1 times B1 shifted left by 16 bits, plus A0 times B1 plus A1 times B0, altogether shifted left by 8 bits, plus A0 times B0. Every partial product is treated as a 16-bit value, and every byte addition explicitly checks and propagates carries. So this isn't just 4 multiplies and a few shifts. The real work isn't in the multiplies themselves, it is in the carry management when those partial products overlap. So that's how we build a correct 16-bit multiply on top of an 8-bit hardware multiplier. Now that you know how we're going to be using the hardware in order to do 16-bit integer multiplication, let's look at the software I wrote to support that. We previously went through this file already, the mathlib16 file that implements the multiplication API, but what we looked at previously was the software path. The core function that we need to look at is literally the core function, multiplication 16 core, but this time we're going to look at it when the version that is going to be compiled when the hardware accelerator is indicated to be used. This is conceptually pretty simple as compared to the software implementation. As you can see, there is no loop in this function. We just do a straight pass through. We do, like similarly to the software implementation, our first step is declare the results variable, but then we go into moving various bytes into the multiplier card. What this instruction is here is moving a 0-page value to a specific byte in memory location somewhere. Since the multiplier card is a memory map device, in order to put data on it, you simply write that data to the address of the various registers within the multiplier card. There are 2 main registers, multiplier A and multiplier B. A is for one of the 8-bit values to be multiplied, B is for the other 8-bit value. And then 2 more registers, which is where you get the results. Once the multiplication is done in hardware, you simply read it out of the address represented by multiplier result least significant byte and multiplier result most significant byte. Remember that when you're multiplying 2 8-bit values, you produce a 16-bit result. The instruction that the minimal64x4 supports to move data from one address to 0-page, which is what we're using right here, only supports an 8-bit movement, so hence the reason why I have to go to each register independently. Furthermore, though I know that they are actually consecutive in memory space, it's probably best not to assume that, hence the reason why I'm doing this by first least significant byte, then most significant byte. Once that's done, you notice that I'm writing the results into a particular location. This is the A0 times B0 multiplication that we talked about earlier. Now we're going to be doing the A1 times B0 multiplication right here. Again, we start off by writing 2 bytes to the multiplier card's input registers for A and B, but instead for the output, we're not necessarily writing those directly to mul results. Instead, we load the byte into the A register, which is what LDB does, and then we add that value into the 0-page location that we need to add the value to that represents the results. You notice that we do this twice. The second time we do it, I use the carry aware version of the add function, such that if there was a carry from this first byte, it gets added to mul results plus 2. And then finally, if that addition operation resulted into a carry, these 2 instructions here then adds that carry into the third byte of the results, such that it's going to be present when we do subsequent bytes. A similar process is used for A0 times B1 and A1 times B1. Ultimately, at the end of these operations, we do have mul results containing all 32 bits of the 16-bit times 16-bit multiplication. And that's simply how it works. Every other aspect of this library, and including the Mandelbrot code, is actually the same. The only difference is if you look at how the preprocessor flag is used, either you're compiling this version of the core function or the software version of the core function. And so given that, let's go see how much more quickly the Mandelbrot program runs when I am using the hardware version of this multiplication core function. Here is the fully built multiplier board. This board is almost entirely surface mount ICs, and that was a very intentional design choice. Using surface mount parts let me keep the overall size of the board reasonable. If I had built this with through-hole components, the board would have been much larger, and routing everything would have been much more difficult. Surface mount construction also lets me keep the signal path short, which is helpful when you have wide, fast combinational logic like this multiplier core. Though admittedly, building this was harder than if I would have used through-hole components. Before any components go down, the first step is applying solder paste. When I ordered the PCB, I also ordered a laser cut stencil. That stencil lines up the pads on the board and lets me apply paste quickly and consistently without smearing it where it doesn't belong. You can see here I'm spreading the paste across the stencil with a small squeegee, making sure every pad gets just enough paste and that nothing bridges between the pads. Once the paste is down, the stencil comes off and the board is ready for component placement. This is the most time-consuming part of the process, especially on a board like this one, which has a lot of small, repetitive logic parts. Most of the board is made up of 74 series logic chips, resistors, and capacitors. Placing these is mostly a matter of patience. Pick up a part, orient it correctly, and drop it on the pasted pads. For a one-off board like this, doing this by hand is perfectly reasonable. But if I was building more than a couple of these, I'd definitely let the PCB manufacturer handle assembly instead. Once the components are placed, the board goes into the reflow oven. During reflow, the board is slowly heated until the solder paste melts. Surface tension pulls each component into alignment, and the solder forms clean joints on every pad. After the oven cycle finishes and the board cools down, you'll end up with a fully assembled board ready for inspection. At this point, I go over the board carefully and look for any obvious issues. Things like solder bridges, misaligned parts, or missing components. Catching those early saves a lot of time later when you start powering up the board and debugging it. One part you'll notice that stands out from the rest is the ATF16V8C programmable logic device. I deliberately kept this chip in a socketed through-hole package, even though the rest of the board is surface mount. The reason for that was development convenience. While I was working on the address to code and timing logic for this board, I needed to reprogram the programmable logic device several times. Being able to pull the chip out of its socket and reprogram it, and then drop it back in, made that process much faster and less frustrating. Okay, now let's test this card in the Mandelbrot 64X4 using it to calculate the Mandelbrot set. See how fast that takes as compared to the software version that we earlier looked at in this video. So let me put this card into place on the card. Turn on the Mandelbrot 64X4. Again, it comes up in a random state, so there you go. Now, as before, I already have compiled and preloaded the software that uses the card onto the Mandelbrot 64X4. So I am just going to run it. I call this ACC Mandelbrot, ACC for accelerated. So let's go ahead and get that started and see how long this one takes as compared to the software version. You can see it already looks much faster than the software version of Mandelbrot. Okay, there it's done with the Mandelbrot image using the Multiplier accelerator card in order to calculate all the multiplications. That certainly did go much faster. I'll put the precise comparison of the two speeds up on the screen in post-production, but I can tell you this was certainly much faster than using the software-only multiplication for calculating the Mandelbrot. So that's the hardware multiplier for the Mandelbrot 64X4. I enjoyed this project. It was a refreshing challenge to try to implement this logic in hardware as opposed to software. I've been implementing software for well over 3 decades now, and to shift this kind of logic into the hardware was fun for me. If you think there is something that I could improve on, please do leave a comment below. I would love to get your feedback. This is the first time I did something like this. This was a learning experience for me. I hope you enjoyed the learning experience too. Before I go, I have one more thing. I still have a few extra of these minimal 64x4 PCBs that I'd love to give away to anyone who would be interested in using it to make their own computer. If you're interested, contact me at the email address that you see on top of the screen right now. Send me your address and then I'll calculate how much it will cost to ship to you. I only ask that you pay for the shipping, otherwise the PCB is for free. That's it for today. If you enjoyed the video, please do like it and leave some comments. I'd love to hear from you. If you like this kind of content, please do subscribe. I don't publish videos often, but when I do like to go in depth like I did today. So that's it for now. Until next time, happy hacking.